Hello everyone. For this lecture, we'll talk about. I want to share some knowledge about. Let's say is count. This page is about proof, argument, and their knowledge. As we know, the knowledge is an advanced topic in cryptography, and it is a famous lecture. And now, if I'm not mistaken, it has been translated into many languages. And this is the first version, and what I want to share is just follow the pace with the open courseware in the MIT course. It opened the open source material in spring 2023, and that course uses this material, and I wanna but that course is a video lecture, including many lecture videos, but this material is as their reading material. Maybe just before the class or after the class, we have to read this lecture to learn about or to command the every section. But what I want to share is just reading. Just through reading this lecture and to fast command it as possible as we can. So I will follow the pace given by the MIT's Advanced Topics in Cryptography course 2023, and in their course website there is for the first course for the first lecture what we should read before the class, and for the second one what we will read, what we should read, and also for the third one and the following lectures. So the first one we'll talk about the 3.1 interactive protocols, interactive proofs. Okay, let me choose a pen. Maybe brush is okay. So I think let's try blue. Today we'll talk about the 3.1 and also 4.1. So let's start with the 3.1. I'm not so familiar with this tool, this software. So first let's find the 3.1. So what is proof? Interactive proof and their knowledge is a very hot topic. So let's start with the 3.1 interactive proofs. Okay, so first let's look at this function f mapping. This there 1 to n, so that means the sequence each number has n bit, and the bit can be 0 or 1 to a finite range R. And key message interactive proof system. So here we know that the interactive proof system, so it must be interactive between maybe two parties. For f, consists of a probabilistic verify algorithm. So we call it V now, running in polynomial time. So with polynomials n and the prescribed honest deterministic proof algorithm P. So here, let's prescribe that the V it is often it must be a probabilistic verifier running in polynomial time. But for the prover, so here we just cite the prover is deterministic prover algorithm P. Okay, so here is P and V. It is interactive, and V is polynomial time, but P is deterministic. Okay, I think I will write very slowly, and to make it very good looking. So both P and V are given common input. So this 0, 1, this is the very common, very universal representation just for input. Basically for almost all inputs we use this form. And at the start of the protocol P, P provides the value y claim to be equal fx. So P provides a claim. The claim is y equals fx. Then P and V exchange a sequence of messages. So sequence of messages M1, M2 to MK. Determined as follows. So let's say how it is determined. The IP interactive protocol designates one of the parties, either P or V, to send the first message M1. So maybe the M1, and then M2 to MK. Maybe there's case interactive turns each with one message. So maybe P is the first sender. Also, V can be the first sender as well. So as party sending each message alternates meaning. For example, if V sends M1, so if V is the first sender, then P sends M2, something like that. Okay, so maybe I should close that. It will be very convenient. Both P and V are sort of next message computing algorithms, meaning that when it is V's turn to send message, okay, it is V's turn to send message. Here V is running on input. V is running on input. X M1, M2 to I minus 1 to produce message MI. Okay, so now it is sending V is sending a message MI. So the message MI should be calculated by the input before MI. Yeah, so MI can be obtained from this input. And the algorithm run in V. Notice that since V is probabilistic, we mentioned that any message MI sent by V. So the message depends on the input before and on the verifier's internal randomness, because it is probabilistic with some randomness. So the entire sequence of key message. Here's M1 to MK, exchanged by P and V, and maybe in K turns along with the claimed answer Y. So here we know that Y equals fx is called the transcript. So both the messages and the claims they form a transcript. At the end of the protocol, the verifier must output either 0 or 1. Here's the it is a must. I think we should know this, because this will go across all the content, that the verifier must output either 0 or 1. With 1 indicating that the verifier accepts the prover's claim that y equals fx. So the prover is to prove that y equals fx, and y equals fx is a claim, and the prover wants the verifier to accept this claim that y equals fx is true, and 0 indicating that the verifier rejects the claim. It means the proof cannot be passed in the verifier. So the value output by the verifier at the end of the protocol, either 0 or 1, may depend on both the transcript T and the verifier's internal randomness. Because there must be a transcript T, and there also must be the verifier's randomness, because it is probabilistic. So here, let's look at the denotion. Denotion is out. Let's clean the Okay, let's clean this. How to clean the screen? Okay, let's continue. This denotion out. Okay, here we can see its output is either 0 or 1, and output on input x. Here x is our input. We're interacting with the deterministic prover strategy P, with internal randomness equal to R. Okay, so here R is the randomness. Okay, R is the randomness. So for fixed value, so first out function, the parameters will be v, p. These are given, and x is our input. R is the randomness of the verifier. So for fixed value R of with internal randomness, so if this randomness is fixed, the output is a deterministic function, so it loses the randomness. It's very clear. So let's look at this definition. The interactive proof system is said to have the completeness. It's because for the zero knowledge proof, for some protocols like the Schnorr's protocol, it has the completeness. It is said to be complete and also sound. With the completeness error and soundness error. Completeness means just the prover and verifier can, just follow their steps to complete the whole protocol step by step. But the soundness is the meaning of reliable. So it is just another representation to say this proof is reliable, and so it is called that it has the soundness. So there also be soundness error. So let's look at this. Is the following two properties hold. So let's say the two properties. The first one is the completeness. So for array x, it belongs to this input. Is the common form, and the okay, first is the completeness. Okay, so the probability must be more than this one, and the delta c. Okay, let's call this delta c. Delta c is the completeness error. So it is the error. So 1 minus this error. This means the success probability. So the probability must be more than this. So the probability of what? It is out. The output x1. So output x1 means the verifier way accepts the claim. Verifier accepts the claim of P, of the prover. So let's look at the soundness. So the completeness, that means the step by step complete the proof and the verification. It's very smoothly and without any problem. So it should be high probability. The soundness is for array. X belongs to this input, and array deterministic prover strategy. Oh, okay. So this P prime. So what is a P prime? P prime is we can think of it as a cheating prover. Okay, cheating. Okay, now it is a cheating prover. Okay, cheating prover is also deterministic prover, and if P prime sends the value. Since value y, but it doesn't equal to fx at the start of the protocol, then the cheating prover also wants the verifier to accept his false proof. Okay, so even if he gives the wrong answer, and he also wants the verifier to accept it. So it is very ridiculous because the verifier should not accept it. So how can this be possible? So let's look at this probability is the soundness. The soundness is how is the probability that the verifier accepts this wrong proof. Okay, accepts the wrong proof. So the probability will be should be very low, very low. So it's less than this value. This value is named just the soundness probability, soundness error. Okay, so here is the value is given that for both the delta C and delta S, they should be less than 1/3. Okay, intuitively for any input X, the completeness condition requires that there be a convincing proof. That is the very successful proof, very smooth proof for what is the value of input X. So there will be no cheating, and soundness condition requires that the false statements, okay, the false statements, just like what we cite of the form fx equals y for any. So here, in this false statement, y will not be equal to fx. So there's a lack of a convincing proof. And there's no cheating for the p prime that can convince the verifier to accept the false claim with probability more than 1/3. So that means the verifier will accept this proof successfully only with probability less than this soundness error. And there will be two costs that we should measure of paramount importance. So the runtime is very important for both P's, as prover's runtime and verifier's runtime. And there are other important costs. Let's say is space usage, and the total number of bits, the bits communicated, and the number of messages exchanged. Now that means the round is maybe we can regard it this as round. How many rounds this protocol will have? And for example, if there will be k messages, just like the claim, the k messages m1 to mk, and there will be how many rounds are there? So there will be k over 2 rounded, k over 2 rounded. Okay, this one means the closest integer. Oh, not the closest. It will be less than this. Okay, less than this, less than. Okay, less than this. The biggest one, less than k over 2, is an integer. So the k over 2 rounded is referred to as the round complexity. So how many rounds are there is represented by this k over 2 rounded of the interactive proof system. So here, the round complexity is the number of the back and forth in the interaction between P as prover and verifier. So if k is odd, so we know that k is odd. So k is odd. That means the maybe the 2p plus 1 equals k. So there will be maybe the final turn in the final message exchange, only one, maybe p or v sends message without any response. Okay, so just a byte with no force because k is odd. Okay, so that's the 3.1 interactive protocol. It's an introduction, and now let's look at the argument systems. Okay, argument system for function f is the interactive proof in which the soundness conditions only required to hold against prover strategies that run in polynomial time. So here's the very important thing. The point is hold against the prover strategies that the prover it should run in polynomial time. So first, it is the interactive. It is the IP. Okay, argument is the IP. So the only requirement is to require this f for f. Okay. So in this f, the soundness condition is only required to hold against the prover strategies that run in polynomial time. Okay. So let's say the difference between this one, between argument system and IP and the interactive protocol. So argument system has some additional requirements. So that's the basic concept. The notion of soundness in definition 3.2, okay, in which the soundness condition. So here the soundness condition changed. It's only required to hold against when should the soundness error should the soundness condition hold. So it is only required to hold against the polynomial time prover. Okay, so here the soundness is called the computational soundness. Okay, so it should be different. It should be contrast with the soundness in definition 3.1. So let's look at the 3.1. The soundness. Okay, here it is the common soundness, and here is our computational soundness. And in our common soundness, the soundness is referred to as the there should be a computationally unbounded prover p prime. So this p prime has the the endless, the infinite power computational resources. So it is called computationally unbounded. Okay, it has infinite computing resources that might be devoting enormous computational resources to trying to trick me into accepting an incorrect answer. So that's the common soundness. It should be that the prime p, the cheating prover has endless resources to trick this way, to trick this verifier. And it is also called the statistical soundness or information theoretic soundness. So this just the name, which we just need to learn about it. But argument systems were introduced by, in 1986. They are sometimes referred to as the computationally sound proofs. So there is an additional computationally sound words. But in this manuscript, we will only use the term proof. Just proof to refer to the statistically sound protocols. So here is the proof. So proof is the statistically sound. So proof means the so proof has the same property as the interactive protocol. They are both using the statistically sound, just our common sound. So it is the common sound protocol. But for argument systems are able to utilize cryptography primitives, and also the argument systems are using the computationally sound proofs. And it can also use the cryptographic primitives. So this is where cryptographic is being used. Will a super polynomial time prover may be able to break the primitive? So that's very possible. It's a super polynomial time prover. So it can trick the verifier into accepting an incorrect answer. A polynomial time prover will be unable to break the polynomial time because it's not super polynomial time. It's only polynomial time, so it may be unable to break the primitive, the cryptography primitive, and the use of cryptography allows document systems to achieve additional desirable properties. So it is the functionality of the cryptography. It has the reusability, and also the public verifiability. So we will not talk about this here. Okay, so this is the introduction we need to learn about. Okay, finally let's look at this explanations as main exception. Okay, here is the concept, the snark. Okay, snark is the succinct non-interactive argument of knowledge. So the basic, I think most of you have heard about the snark. It's very popular word in DKP's knowledge proof. It means the succinct is very brief and short proof. Because the prover want to prove something to the verifier and desire the verifier to accept it. So this proof should be short and easy. So this is succinct and non-interactive because we just add interactive protocol. Okay, so it needs the interactive, but here we don't need the interactive, so it is called non-interactive. So it simplifies the communication process and argument or argument system. Okay, we just argument systems. We just explain this of knowledge. Okay, so it has the most important properties. The first is brief and short, easy to verify, and the other is non-interactive. Okay, this is our sharing of 3.1 and 3.2.